Professor Ray here, and today we're going to do a portrait or a profile of an American scientist and inventor named Joseph Henry. Now, his name may or may not sound familiar to you, but because of his work, we benefit from lots of things around our house. Anything that has an electric motor in it, basically. So that can be things like a drill. And later on in this presentation, I'm actually going to take a drill apart and show you what's inside of it. It can also be things like a blender. It can be a hair dryer. It can be a refrigerator, anything that has a fan. It's all because of electric motors. So how did he do this? He made some correlations between electricity and magnetism. Now, electricity and magnetism are both different, yet they are interrelated. And it was Henry who really started putting all these pieces together. Specifically, what he did, he leveraged some work by a Danish physicist named Hans Christian Ørsted, who showed that an electrical current passing through a wire created a magnetic field. Ørsted noticed this by accident. He was passing the current through a wire, and he had a compass sitting nearby, and he noticed the needle on the compass deflected. So he knew that he had created a magnetic field. But also, a moving magnetic field can go the other way and create an electrical current in a wire. So like I said, electricity and magnetism, they're both different, yet they are very related. And I'm going to do some experiments later on in this video to show you how they relate to one another. But back to Joseph Henry. He was born in Albany, New York in 1797. His family was very poor, and his father actually died when he was a very young man. He was sent to Galway, New York to live with his grandmother who would raise him. Now, a lot of people might have thrown up their hands and given up with such adversity in their life, but Henry did not. In fact, he was very hardworking, very studious in school. He worked at a general store. He was an apprentice as both a silversmith and a watchmaker. He tried always to learn more and more, and that got noticed. In fact, he ended up getting a full academic scholarship to the Albany Academy in Albany, New York, which, by the way, is the state capital of the state of New York. So at Albany, even though he had a scholarship, he didn't have any money for room and board. So he actually taught at the school while he attended, and that's how he paid his way through. And after 7 years, I guess he got the equivalent of what we would call a doctorate degree. They named him the Professor of Mathematics and Natural Philosophy at Albany. But that would just be the start of his illustrious career. Later on, he would take a similar position at Princeton University. And then even beyond that, he became the first secretary of an institution known as the Smithsonian Institution in Washington, D.C. So he went from this adversity, he accomplished great things during his life. So some other things he did, back in the 1800s when he lived, a lot of commerce was conducted by shipping. And if you think about ships, what are they concerned about? They're concerned about the weather, and they're concerned about where the coastline is. They want to be able to anticipate weather, and they don't want to run into the coast. So he was actually one of the founders of the National Weather Service and the National Lighthouse Service to help the shipping industry be safe. So he had interest in many subject areas, like I mentioned, and some of those even included theater. So it's okay if you're a technical person to be interested in the arts. Henry showed that. But it was really this electromagnetics that piqued his interest. And if you are interested in electromagnetics, you would get that typically in a major in college called electrical engineering, and you would study it. You would actually take a whole class on electromagnetics, which is just steeped and lots of equations using advanced calculus. So that's why it's important to learn math. For electromagnetics, that's the theoretical end, and the more practical end would be electromagnetic and electromechanical machines, which teaches you how to put the electromagnetics to work to make things like motors and generators. So one of Henry's inventions was called an electromagnetic relay switch. And what was important about that was not that invention so much, but Samuel Morse took that invention and created the telegraph from that one invention. So that now we could open up communications by sending coded messages over wires using an electromagnetic switch. Henry also invented an electromagnet capable of lifting 750 pounds with a fairly modest battery. So the key to both of these inventions is what was called electromagnetic induction. And that's what we're going to talk about. And there's some examples of components in electrical engineering that called inductors. And here are several of them. These are used in electrical engineering and electronics, and they have coiled wire, you'll notice, and terminal strips. Another example would be a transformer. I took this out of a bug zapper that failed, and this uses electromagnetic induction as well. So in 1875, Henry was introduced to a gentleman I think you probably heard of. His name was Alexander Graham Bell. And Alexander Graham Bell showed him his very first prototype for a telephone. Henry looked at it and said, you know, you've got the germ of an absolutely great earth-changing idea here with this, but I would not publish anything until you get it perfected. Alexander Graham Bell said, I just don't have the knowledge to know how to perfect it. So Henry, having been a professor and probably a little on the stern side, basically ordered Alexander Graham Bell, well, go get the knowledge that you don't have so you can make it perfect. A year later, he had perfected the telephone. So one of Henry's inventions was the electric motor, but it's not a motor like we think of today. He used electromagnetic induction just to cause a pendulum-type motion, an object swinging back and forth. But what he showed is that you can use electricity and magnetism and you can create motion. Others would take that and put it into a form that could create rotational motion like we have in the blender and the drill. So although his invention was very crude, it was a good starting point. And we'll do a few experiments just to show you how all these different pieces we've talked about so far tie together. For the first experiment, we're going to talk about just magnets. And I've got this real flimsy box right here, and I want to show a couple things about magnets. I have two magnets here, and I'll put one here. And magnets have poles. They have a north pole and a south pole. And like poles, like two north poles, would repel one another. And unlike poles, a north and south pole would attract one another. So that actually gives us something we can work with when we start talking about motors. I have one magnet here. I'll take the exact same pole and we'll try to flex it, and you can see it pushed it away. So we had like poles repel one another. So now I'll take that magnet, I'll turn this over. Unlike poles attract. So we have attraction and repulsion. We can use that when we get into the study of motors. Now we're going to show how electrical current moving through a wire can cause a magnetic field to be created. And what we're going to do is basically reproduce the test that the Danish physicist Hans Christian Ørsted did. So I will carefully move a compass over here. I have a source of electricity. I have four 1.5 volt batteries, so I have 6 volts total coming off of this. And what I will do is carefully lay this cable near the compass, and when I connect this, a current will flow and create a magnetic field. And there we can see the compass is moving. And that's showing that we have a magnetic field going through this wire and causing this current to flow. So we basically have shown that an electric current flowing through a wire creates a magnetic field. Next, I want to show if we move a coil of wire in a magnetic field, we actually create electrical current flow. And the way I will show this is I'm going to take an old motor. This probably came out of a toy of some sort. And I'm going to take a voltmeter. And right now it says 0 volts. On the back of this motor are 2 little contacts. They're copper contacts where wire would normally be soldered on. I'm actually going to hold the probes of the voltmeter on there and then spin the motor, and we should see a voltage appear on the meter. So there I have the contacts on, and I will spin the motor, and indeed we see a voltage appearing on the voltmeter, and if I go the opposite way, a negative sign pops up, and that shows that we have an opposite polarity voltage. So all I'm doing is creating voltage by moving electrical coiled wire in fixed magnetic field. This has fixed magnets inside of it. That's how we're doing this. Finally, I'm going to show you how to make an electromagnet for lifting up metal, much like Henry showed. I have some nails here, some of which are steel and should be picked up by the magnet, the electromagnet. And I just took a piece of steel. This is a hole punch that's used in carpentry. And I took some green wire. I just wrapped it around to create my inductor. And when I put voltage to it, it will become an electromagnet. And just to show you, nothing's coming out when I touch the electromagnet inside. So let me connect the voltage. And again, this is just 6 volts DC. And this time, we got 1 out. We've got several nails out. So we've created a magnetic field. And by using these coils like this and putting this metal in the middle, we've actually concentrated the field and made it pretty strong for what we have. There we go, an electromagnet. Remember, Henry made one that lifted 750 pounds. So now we're going to take a look at a drill motor. I've taken this one apart, and I've actually removed the handle on the back so we can see how it works. The first thing I want to show you is that there is a device inside called the rotor. This is the part that rotates and drives the drill bit. And it has these contact points, and electricity comes in and contacts these through what are called brushes. They're spring-loaded devices. Up in here, they push down on these contacts. Alternating current comes in through here, creates a small magnet on 2 sides. So we have a magnetic field created on the rotor, but we also have these coils here. These are called the stator. And the stator does not move, but because alternating current is coming in, the magnetic field moves as well. We showed earlier that magnets can attract or repel. These are designed to set up so that once they get running, the attraction and repulsion causes the drill to spin and causes the drill bit to spin. What we have on the front end of the drill is a gearbox. This creates the torque. It takes the rotary motion from this rotor, goes through gears, and creates the torque we need so it will bite into the material and drive the drill bit in. I will pull that off and show us what that looks like. And there's an example. We can see the gears up inside of the gearbox on the front of the drill. So on the rotor, the shaft of the rotor in itself has gear teeth on the very end. So I'll carefully remove this front piece, slide it out, and there is our rotor inside the drill, and we can see that is what spins and ultimately goes through the gears and drives the drill. This is actually a fan, and it's used to pull air through to keep the drill cool. And when it's all assembled, there are slight vents around the outside that allow the air to come in. What I'm going to do now is pull the rotor out, and when I do that, you will see these brushes pop loose and they'll drop down in. They will no longer contact the backside of the rotor. So when I pull those out, there the brushes just drop down. And here I'll show the inside of the drill. These are the field coils or the stator. The alternating current causes the magnetic field to rotate inside the drill. When this goes in, electricity comes in, pairs of these that are opposite from one another, creates individual electromagnets, and based on whether they oppose or attract, it causes this to spin within this magnetic field. So basically we have this motion, this rotary motion caused by the magnetic fields ever changing inside the drill. So if you ever wondered how a drill worked, that's what goes on inside. So we have the stator, which is the constant, the static coils, if you will, that causes the rotational magnetic field. We have the rotor, which actually can spin inside, and the magnetic fields attract or repel, cause the spinning, which then drives this gear, which then connects to these drive gears and causes the drill bit to spin. All of this because of Joseph Henry and his work with electromagnetism and mutual inductance.